Advances in Geotechnical Instrumentation. Welcome to Blueprint to Reality, the channel where civil, structural, and geotechnical engineering concepts are explained clearly and practically. In today's video, we'll explore advances in geotechnical instrumentation, the modern tools engineers use to understand what is happening beneath the ground surface. From smart sensors and real-time monitoring to data analytics and artificial intelligence, you'll see how modern instrumentation is transforming geotechnical engineering and making infrastructure projects safer and more reliable. 1. Introduction. Geotechnical engineering deals with soil, rock, and ground behavior, which are naturally variable and uncertain. Because we cannot see what happens underground, instrumentation plays a critical role in understanding ground performance. Geotechnical instrumentation refers to the tools and systems used to measure, monitor, and record soil and rock behavior during construction and throughout the life of a structure. With rapid technological progress, modern geotechnical instrumentation has become more accurate, automated, real-time, and intelligent. 2. Why geotechnical instrumentation is important. Instrumentation is used to verify design assumptions, monitor safety during construction, detect early signs of failure, control construction quality, reduce risk and cost overruns. In projects like dams, tunnels, deep excavations, slopes, foundations, and embankments, instrumentation is often the only way to ensure long-term stability. 3. Traditional versus modern instrumentation. Traditional instrumentation. Manual readings, limited data points, time-consuming data collection, higher human error. Examples: standpipe piezometers, mechanical inclinometers, settlement plates. Modern instrumentation. Automated and continuous monitoring, real-time data transmission, remote access integration with software and AI. This transition has transformed geotechnical engineering from reactive to predictive. 4. Advances in pore-water pressure measurement. Vibrating wire piezometers. High accuracy and long-term stability, resistant to electrical noise, suitable for dams and deep foundations. Fiber optic piezometers. Immune to electromagnetic interference, can operate in extreme environments, suitable for large infrastructure projects. Wireless piezometers. No long cable networks, faster installation, ideal for remote or hazardous sites. These advances allow engineers to monitor effective stress changes in real time. 5. Advances in deformation and displacement monitoring. Automated inclinometers. Continuous monitoring of lateral ground movement, critical for slopes, retaining walls, and excavations. Shape acceleration arrays, SAA. Measure full deformation profiles, provide real-time displacement data, high resolution and reliability. GNSS and GPS-based monitoring. Used for large-scale ground movement, suitable for landslides, embankments, and mining areas. These systems significantly improve early warning capability. 6. Settlement monitoring innovations. Hydrostatic level systems, HLS. Measure differential settlement with high precision, widely used in tunnels and bridges. Magnetic extensometers. Track settlement at multiple depths, useful in embankments and soft soils. Automated total stations. Robotic instruments for surface settlement, high accuracy and continuous tracking. Modern settlement monitoring minimizes unexpected structural damage. 7. Fiber optic sensing technology. Distributed fiber optic sensors, DFOS. Measure strain and temperature along entire cable length, thousands of data points from a single fiber. Applications: slope stability, tunnel lining, deformation, pile load testing. Fiber optic sensing represents a major leap in spatial resolution and durability. 8. Wireless and IoT-based instrumentation. Internet of Things, IoT, in geotechnics. Sensors connected through wireless networks, data sent to cloud platforms, engineers access data from anywhere. Benefits: reduce site visits, faster decision-making, improve safety. IoT enables smart geotechnical monitoring systems. 9. Role of data analytics and AI. Modern systems integrate big data analytics, machine learning algorithms, predictive modeling. Applications: detect abnormal trends, predict slope or foundation failure, optimize maintenance schedules. This shifts geotechnical practice from monitoring to forecasting. 10. Challenges and limitations. Despite advances, challenges remain. High initial cost data overload need for skilled interpretation sensor durability in harsh ground conditions. Instrumentation is effective only when properly designed, installed, and interpreted. 11. Future trends in geotechnical instrumentation. Fully autonomous monitoring systems, AI-driven decision, support integration with BAM, and digital twins, more affordable wireless sensors. The future points towards self-learning geotechnical systems. Conclusion. Advances in geotechnical instrumentation have dramatically improved our ability to understand, monitor, and predict ground behavior. Modern tools provide real-time data, enhance safety, reduce uncertainty, and support smarter engineering decisions. As infrastructure projects become larger and more complex, advanced instrumentation is no longer optional. It is essential. Advances in geotechnical instrumentation are changing how engineers monitor, predict, and manage ground behavior in modern infrastructure projects. If you found this video useful, like, share, and subscribe to Blueprint to Reality for more clear explanations on civil, structural, and geotechnical engineering topics. Let us know in the comments which topic you'd like to see next, and keep learning how engineering ideas move from blueprint to reality.